putting the chemical shift evolution, one can see. For example, IZA goes to, by 90-degree pulse to IXA, and I put this precession and J, and then I get IXA cos plus IYA sine, and using this property, I have IXA cos pi JT1 plus twice IYA IZB sine pi JT1, and apply a 90-degree X pulse, and then I get IXA cos pi JT1 minus twice IZA IYB sine pi JT1. And this says this is the diagonal peak, and which is in phase, and a cross peak which is the anti-phase. The steps.
In general, is this treatment restricted to spin 1/2, or is it only that just that those identities?
Okay, it's not restricted to spin 1/2 only. The only difference is that this simplification is different for spin 1, for example. And so you have to find. I think people know about spin 1. I am not quite sure as to how far it has gone beyond that. Okay. Now, the product operator method is actually somewhat similar to our vector diagram, and except that it's a bit better. And what I've done here is I just use this product operator method that I just told you and superimpose it upon the vector diagram picture. And then we see that we can follow quite a bit. That is, we had a Z magnetization of spin A. We applied a 90-degree pulse along x-axis. We got an IYA. The IYA processing under J gives me IYA cos pi JT1 plus twice IXA IZB sine pi JT1. This we have to build in at this point. And then we apply, for example, a 90-degree pulse along the y-axis, and then it converts, gives me IYA along the y-axis, and it gives me IZA, IZB along the Z direction. And this is interesting, because this is what we did not see in the previous analysis. I have now thought of putting a 90-degree pulse only on the spin A. So I'm converting this into purely a Z magnetization at this point of time. IZA, IZB. And then when I put the B pulse, I convert into antiphase B magnetization. Antiphase with respect to spin A. And so this picture, the vector diagram picture, can be thought of as being quite right, and it is just these operators are represented in terms of vectors. For a two-spin system, one can see the result on this, and I have these results in slides. The first slide shows you. May I have the first slide, please?
Yeah.
Is that okay? It is showing us the calculated spectrum of two spins A and X coupled to each other, and this is the diagonal part, which is in this particular pulse scheme is the is dispersive, and this is also diagonal, and these are the cross peaks which are absorptive and antiphase. These ones are going down, and these two are up. The next slide shows the experimental spectrum, but it is an absolute mode spectrum. And so we see that these are the diagonal peaks, these are the diagonal peaks multiplets, and these are the cross peak multiplets. You might notice that particularly in the previous, in the next one maybe, that this is the phase sensitive spectrum, and here this is an experimental spectrum, and the similarity of this with the calculated spectrum is quite remarkable. And we have the diagonals here and the cross peaks here. And you see the cross peaks are of about the same intensity as the diagonal peaks, 1, 1, 1, 1, except that along the diagonal it's slightly different between these two, and this is because of this little bit of strong coupling mixed into it. But what I would like to remember at the moment, that the cross peaks have about the same intensity as the diagonal peaks. Okay. But suppose what I started doing here at this point, I started reducing this coupling constant, or these lines were broad for some reason, then these will start overlapping and cancel each other. And in such circumstances, what happens is the diagonals are big and the cross peaks are small. And that's one of the problems of COSY. Thank you for the slides.
The ridges you see are just artifacts, experimental.
Let me go back. Can we have the slide again on the next one? Okay. Oh yes, the ridges are the experimental. These are tails. As we saw that even in calculated spectrum, these come from the dispersive components of the Lorentzian. Of the Lorentzian. And they are the greatest nuisance that we have, and that's the reason one has to use very strong filtering in these experiments and kills the signal to noise quite a bit. If one had only pure absorptive and converted some of these cross peaks, line shapes from, for example, a Lorentzian to a Gaussian, you'll have very, very little ridge.
But it's not noise, it's real. It's just that's the shape of the dispersive.
It's calculated spectrum also.
Yeah.
These ridges were the ones which created a lot of difficulty in the beginning, particularly in applications to biological systems where signal noise was a problem. Okay, that is the two-spin system, COSY spectrum. I show you a calculated spectrum, or not calculated, just schematically drawn spectrum for AX2 spin system, or A2X or AX2 spin system, which will have this pattern. A2X has a doublet for the A2 and triplet for the X, and therefore there are 9 peaks in the X region, and there are 4 peaks in the A region. The cross peaks are somewhat interesting. The central peak is missing here, including this, because there is an antisymmetric transition which cancels its intensity with the symmetric transition, which has opposite intensity in this case. There is a particular way of displaying the phases of these peaks here, and I will briefly go through this here. The A and the B are the components of the that the A and B we defined earlier from the absorptive and the dispersive components. And the angle phi is a resultant of these two, and the phi is the angle between the resultant and the B direction, and that can define the phase of the pulse. For example, if the angle is an arbitrary angle, we will have a mixed phase of this peak. If the vector is pointing in the plus x direction, that means B is equal to 0, and it's a purely absorptive line shape. If it is in this direction, it's a purely absorptive, but with a negative sign. On the other hand, if it is pointing down, it's purely dispersive with a positive dispersion and a negative dispersion pointing up. Therefore, what we see here is that these peaks are dispersive, pure dispersive. These peaks are absorptive, pure absorptive. And so we have a pure spectrum, pure cross peak absorptive and pure dispersive cross peak. Same character as in the two-spin case. This is only for weakly coupled spins. Okay? For AX3 or A3X, the spectrum is more complicated and has somewhat similar behavior, except that if you look at the A multiplet, all the lines have equal intensity. Again, they are antiphase, and they cancel each other if they are overlapping, while not the diagonals. For strong coupling, we can't use product operator. We are back to using density appreciator. If you have a strong coupling, a second order coupling in the spectrum, if you need to know how the spectrum will look like, you have to go back to the algebra that I put forward to you a few minutes ago, and you have to use the calculation in the eigenbase. And therefore, you'll have to calculate the matrix Ix and Px or Py in the eigenbase. And then for two-spin system AB, it's straightforward to see that this is what is going to happen. And the calculated spectrum is given on this transparency. And please don't look at the right-hand side of this, because that we will look after we study multiple quantum transition spectroscopy. And what it says is that the spectrum of two strongly coupled spin system will look something similar to what we have for weakly coupled, except that we have, for example, the intensities along this diagonal will show smaller, larger, and larger, and smaller, while the cross peak will not have, this part will have same 1, 1, 1 intensity. On the other hand, on the other side of the omega 1, the diagonal has same equal intensity, but the cross peaks have the strong coupling pattern. Okay, and this causes mixing of phase. For example, one can see that this peak is purely absorptive, purely dispersive, while this peak is purely absorptive. It has the same intensity in both the plus omega 1 and minus omega 1. On the other hand, this peak has mixed phase, and the amount of mixture of phase is dependent upon mixture of the eigenstates. So the mixed phase of the peaks is on the diagonal and on the anti-diagonal, if I may call it. This one is anti-diagonal. Okay. At this point, we come to the end of our understanding of magnetization transfer from one spin to another, how a cozy spectrum is generated. And so, for those people who don't want to read this part, it's perfectly fine. You can ignore this and come to the result directly. Okay, and the result would look something like this. And we are now going to talk about the applications of cozy. Okay, the result looks very illustrative. Actually, it's very pictorial. The two-dimensional NMR spectroscopy is extremely pictorial. Okay, and here is the cozy spectrum. We went through a very great labor just now to see why there will be a magnetization transfer from one spin to another. We have come to the conclusion that there will be a magnetization transfer if there is a J coupling between the spins, and if we will resolve that. If we will not resolve it, we still will not see a magnetization transfer. The other conclusion that we have is that the magnetization transfer is not a net magnetization transfer. It is only a differential transfer. So with this information, we can go ahead and use the cozy. And so here we have an example of an application. A very simple one-dimensional spectrum. You can record perhaps on A60. The spectrometers that were designed in the 50s will give you a spectrum like that. And the question is, which line belongs to which proton and which ring, for example. And you will have to do some decoupling experiments if you wanted to sort it out, to which line belongs to which proton and or to which ring. But you run a cozy on that, a simple cozy, and you get the answer in a pictorial form, which says there is one system here, not coupled to another, and these all transitions belong to this ring. There is a peak here, which is coupled to this one, but not to anything else. So there is one ring system here, and there is another one which is here. Okay, so the three ring systems are separated out in a very illustrative way by a simple application of cozy. A slightly more complicated spectrum will look like something like this. That is the one-dimensional spectrum, and again the question is, which line belongs to which proton in this molecule? Okay, one thing, run a cozy, and you see what it has as a result. First thing that you notice in the cozy is there are two lines which are mutually coupled and not coupled to anything else. So they must belong to this ring, separated out ring. And so these are the alpha and the beta protons. And then we can start somewhere. Let's see, this peak looks very isolated. Let's look at this one. And this happens to be this proton, but this we know only at the end. But this it's coupled to only one more peak. It has one cross peak only. And suppose this was this one, as it is, then this would be, if this was called F, This will be the E. Then we look at the E. It has another cross peak at this end. So that is the D resonance. And the D has another cross peak, which is the C resonance. And the C has another cross peak, which is the B resonance. And B has one more cross peak and the A resonance. So basically you can walk along this cozy spectrum and do the assignment. And it's essentially one experiment, one set of experiment which you give the instruction to the computer, run it. You don't have to know where should I radiate, how much power should I use, because the 90-degree process is the same for all. So it's indeed, I must tell you that it's easier to run a cozy than a decoupling experiment. Well, the situation gets complicated when you come to larger molecules, and this is a cozy of a protein, and it doesn't matter which it is, but it has very well identified regions where one can look for cross peaks, for example. This is the region in which the A part of it is the region in which the non-labile, side chain, non-aromatic side chain resonances give resonance signals and cross peaks among themselves. Okay, a complex region. The region, this one, gives us cross peaks between the alpha and the beta, or alpha and the methyl protons of alanine and threonine. The C part, this one, and also the D part, I should combine all of it, give us cross peaks between the alpha and the beta resonances. The E part gives us some more cross peaks within alphas. For example, glycine has 2 alphas. Those cross peaks will lie in this region. And this F region is the one in which the aromatic protons will give cross peaks to each other. The interesting region is the G region, in which, okay, this is symmetric. I should have said that. This cozy spectrum is always symmetric about the diagonal, because I didn't bring that point in. If there is a transfer from spin A to B, there is a corresponding transfer from B to A. Okay, and so it's always symmetric. Experimentally, it will not look symmetric, because there will be noise, there are other characteristics, but in its information content, it is symmetric. And so you have a region, G region, which is from the NH protons, the amide protons, to the alpha protons. And this region is a very useful region because, and it's called the fingerprint region, because basically we get one cross peak per residue in this region. And it is the starting point of assigning a protein. And the fingerprint region is which we often look at in great detail. And this is the fingerprint region of maybe the same of BPTI, and this is the stack plot form. Good for looking but not using. The using part of it is from the contour plot form, and you can see the kind of sophistication has gone into this business. Every single peak here has been assigned to the various residues in the protein. This is an absolute intensity plot, and a phase sensitive plot has higher resolution, and also you can notice the multiplet of the cross peak. There are 4 peaks here, which are not visible, for example, in an absolute intensity plot, but they are better visible in the phase sensitive pure absorptive plot. So phase sensitive plots are very useful. This is further exemplified in this picture, where this lower one is an absolute intensity plot of a and you see the cross peak has some structure you can still see, And if you take a cross section at this point, you will get a peak which will look like this, which you can see the doublet here and a doublet here. So it is actually a doublet of a doublet here, but the structure is not very well visible. But when you go to the phase sensitive plot, it is very clearly visible that there are 16 peaks here. And so phase sensitive plot has a very high resolution. Maybe this picture is not there with you. It is possible.
Yes,
is it there with you?
Number 15.
No?
Number 15.
Oh, it is 15. Okay, it is there then. Let me see. Yes, it is there. 15 is there. Okay. All right. So you can see that the phase sensitive, a pure absorptive phase sensitive spectrum has very high resolution and is extremely crucial. In fact, that's perhaps the difference between the first half of 1980s and second half of 1980s, the phase sensitive plot.